Number 1, hypothetical. Does coaching for the math SAT work? A group of 200 high school seniors volunteer as subjects for an experiment. 100 are selected at random for coaching and 100 are controls. After 6 months, all 200 subjects take the math SAT. A box model is set up for this experiment as shown. So student 1 is either going to be in the coaching box or the control box all the way up to number 200. So letter A, John Doe participated in the experiment. He was student number 17. He got assigned to the coaching group. There was a ticket in the box for him. Did this ticket have one number on it or two numbers? So the box, what does the box do? It puts them into a group. Okay, so basically if you draw out a number 1 through 100, you end up in the coaching box. If you draw out number 2 or 101 to 200, you end up in the control box. So it would just have a single number on it. So he draws out the number 85. Where would he land? Coaching. Okay. His sister, Jane Doe, also participated. She was student number 18. She was assigned to the control group. Oh, anyway, my numberings were wrong. No coaching. Did her ticket have an A number on it? If so, what does this mean? So she ended up in the control group, so what did she draw out? A B. Right? The coaching group averaged 486 on the math SAT with an SD of 98. The control group averaged 477 with an SD of 103. Did coaching work? Well, if a reporter saw this, they would run out and say that coaching increases your score by 9 points. Right? Is that true? Well, we don't know. So the coaching group got 486. That was their average with an SD of 98. And the control group had an average of 477 with an SD of 103. So what is my null hypothesis going to be? The difference is equal to 0. Now you could set that up in a lot of different ways. You could say that 486 is equal to 477. You could say the difference is equal to 0. You could use words, that the coaching group was equal to the control group. It doesn't really matter how you set it up. The point is to determine, are these different or not? Okay, so the alternative hypothesis says the difference is greater than 0. Could I say less than 0? Yeah. It just depends on which side of your subtraction is going to be. But we might as well keep everything positive because all of our tables are positive. So I'm going to do coaching minus control. But if you did control minus coaching, then you would just say less than 0. Okay? So on the curve, 0 is the expected value. Or yes, the expected value. And we ended up with a difference of 9. That's what you get when you take 486 and you subtract 477. Okay? So we need to figure out how far away is 9 from 0 in terms of the SE difference. How do I compute the SE difference? Well, I have to divide this by square root of how many people were in each group? 100. So in both cases, D was 100. Do I need to use the t-table? No, and in fact, I don't think they do 2-sample t-tests in this book when the draws are less than 100. Yeah. So I'm going to divide this by the square root of 100, or just divide it by 10, and I get 9.8. And I'm going to divide this by 10, and I get 10.3. Now what do? I do the square root rule, which is the square root of the first squared plus the second squared. What do I expect my answer to be? It's got to be smaller than the sum, so it's got to be smaller than about 20. But it also has to be bigger than the average, and the average is about 10. So it's got to be somewhere between 10 and 20, probably about 15. So we take the square root of 9.8 squared. We add that to 10.3 squared. And I get 14.21, which is what we should expect. Okay? So now, how far away is this compared to 14.22? So I take 9 minus 0, which is 9, and I divide it by 14.22. So 9 divided by the answer. And I get a z-score of 0.63. So in this case, am I going to accept or reject the null? Accept the null. But we have to find the p-value because the world doesn't understand statistics. So I clear my draws. And I shade norm from 0.63 to 5. Wow, I don't know where I am. Shade norm from 0.63 to 5. And I get a p-value of 26.4%. 26.4% is larger than 5, which means I accept the null, which means coaching didn't help. Did I get something wrong? So, okay. So if p is greater than 5, we accept the null. If p is less than 5, we reject the null. The reason is, if my p-value is very small, that means that I ended up on one far edge of the normal curve. How likely are you to end up on the far edge of the normal curve? Very unlikely. So if we land in the middle, that is expected. If we land on the edge, that is unexpected. So in this case, if you look at the normal curve, we landed like right here, where this area is 25%. How likely are you to land right there on the normal curve? Pretty likely. Okay? So is it crazy to think that we would have landed there? No. That sort of thing happens all the time. So we would say, oh, there's no difference between those two tests. Okay? Now there is a difference. There was a 9-point difference. But that difference is totally explainable by chance. If I did this again, and I got over here where the area is like 1.3%, how likely are you to land there? It's very unlikely. So if we did land there, that means that this number 0 is probably not correct, because there's a very small chance that we land that far away. And where is the line? The line is generally accepted at 5%. So if we land outside on the edges, less than 1%, then we suspect that the average is in the wrong place. Basically, we're saying we're using the wrong curve. The original curve was not true. But if I land in 25%, that's close enough to the number that we say, oh yeah, that's totally reasonable. So if your p-value is big, we accept the null. If your p-value is small, that means we landed so far away that we think the middle number is wrong. Does that help? Okay. Number 2. Is Wheaties a power breakfast? A study is done in an elementary class. 499 students agree to participate. After the midterm, 250 are randomized to the treatment group and 249 to the control. The treatment group is fed Wheaties for breakfast 7 days a week. The control group gets sugar pops. Final scores average 66 for the treatment group with an SD of 21, with a D of 250. And the control group had an average of 59 with an SD of 20, and D in that case was 249. So does it appear that Wheaties helped? Well, I don't know. We're going to say the null says that the difference is equal to 0, and the alternative says that the difference is greater than 0. So I draw my curve. I put 0 in the middle. The actual difference is 7. So how far is that in terms of an SE? Well, we have to take the square root of 21 divided by the square root of 250, and then square that, and add that to 20 divided by the square root of 249 squared. So this is the SE for the left side, and this is the SE for the right side, and I squared them both and put them in a square root. Yeah, I did it all in one, and notice where I put the parentheses. This only works if you put those in the right place. So I hit enter, and I get 1.83. So my SE for difference is 1.83. Before I do anything else, what do you think? Reject the null, right? That SE is pretty small compared to 7, so we'll probably reject the null. Let's check. So 7 minus 0 divided by 1.83 is 7 divided by 1.83, and I get a z-score of 3.81. So clear my draws, shade norm, and I'm going to shade norm from 3.81 to 5. And I get a p-value, which represents this area here, of 6.9 e to the negative 5. So that's 0.000069. Okay, what does that mean? So our area is less than 1%. So I reject the null, and I accept the alternative. What does that mean in the context of this problem? Does eating Wheaties help? Yes, compared to sugar pops. Good question. So, this control group wasn't really a control group, right? A control group would be just do what you do normally, right? We're not going to change anything with you. So really what they're doing is comparing Wheaties and Sugar Pops. And apparently Wheaties helps and Sugar Pops hurts. Well, we don't have a baseline, so we can't say it hurts. We just say Wheaties performed better than Sugar Pops. So the next part is, what could have been done blind? Can you feed cereal to somebody and make it blind? Well, you could blindfold them. Would that help? Not really. How come? Because they can still taste and smell it. Okay? So double blind means the person receiving the treatment is blind and the person giving the treatment is blind. So does it do any good for the teacher to be blinded? Could you make the teacher blinded? You actually could. So if I look out here and I don't know who's eating Wheaties and who's eating Sugar Pops, then I am considered blind. So you can make the administrator blind, but there's no way to make the subject blind unless they can't taste and can't see. What part are you looking at? So it would be 66 out of 70 or whatever quiz or test they're talking about. No, it's a result from some assessment. It's their score. Yeah. Yep. So they ate Wheaties for weeks and weeks and weeks while they learned something, and then when they were tested, their score was 66. We don't know what it's out of, but it doesn't really matter. All right. Is this coming together? A little bit. Number 3. Midterm scores averaged 61 for the treatment group with an SD of 20, and then 60 and 19. So we had 61 and 20 and 60 and 19, which means halfway through this experiment, the Wheaties people scored 1 point more than the Sugar Pops people on the midterm. Okay. Just looking at this, what's the result going to be? Accept or reject the null? We're probably going to accept a null because that difference is really small compared to the ST. Once again, this was D equals 250 and D equals 249. So my null is that the difference is equal to 0, and the alternative is that the difference is greater than 0. So I draw my normal curve, and I put a 0 here and a 1 there. Now I just need the SE difference. Well, I need to divide this by the square root of 250, and I need to divide this by the square root of 249. Then I need to add the squares of those together, and then I need to take the square root. And I'm going to do all of that in one big swoop. Okay? Now, do statisticians really do this every time? No. No. They do an electronic survey, and they get all of this information electronically, and and then they can either just plug in the numbers and tell the computer do a 2-sample z-test, or if their software is more fancy, you just get all of the scores for the midterms, for the treatment and the control, and you just say do a 2-sample z-test, and it will spit out a p-value immediately. Yes. So all a statistician really has to do is write the surveys, collect the data, and then tell it which test to use. And everything else is just done by a computer. Now, we don't have that luxury. We've got to actually figure it out. So the square root of 20 divided by the square root of 250, and then I'm going to square that, plus 20 or 19 divided by the square root of 249, and I square that, and I get 1.74. Okay, so 1 minus 0 is 1 divided by 1.74. And that gives me 0.57. So my z-score is 0.57. So I clear the draws, and I do a shade norm from 0.57 up to 5. And that gives me a right-tailed area. This area over here is 20%. So actually, it looks more like this. So, accept or reject the null? Accept. Okay. Is this difference, so the Wheaties kids scored 61 on average. The Sugar Pop kids scored 60. Is the difference between those two significant? No. They're close enough to each other that it might just be chance error that gave us that 1 point advantage. So we accept the null and we say there is no significant difference on the midterms between Wheaties and Sugar Pops. And you'll hear that on TV or you'll read that on the internet. And it will say there is no significant difference between this shampoo and that shampoo. Does that mean there was no difference? No. There was probably a difference, but the difference was not large enough to be called significant. And significant is the 5% p-value. So whenever you hear that word significant, it means something in statistics. And nobody understands that, right? Reporters don't get that. They don't understand significantly different. They just look at the numbers. Oh, hey, 61 and 60, the Wheaties kids did better. They did 1 point better. But a statistician would say, there's no significant difference. There was a difference, but it's not significant. Or in the case of the 1% model, it would be highly significant. Oh, there were probably a whole bunch of things to say. What do we conclude? We conclude that anyway, we answered that. B. Repeat, if the average midterm score for the treatment group is 68 with an SD of 21 and 59 with an SD of 18. So that gives me a number here of 68 and 59. That is 9. And I need to go back. I'm going to go back here and just change some of these numbers. So we need to change the 20 to a 21. 21. And then the 19 becomes an 18. And then I run that. Oh, not 198. That's definitely not right. I thought this would be faster, but now I'm changing my mind. Okay. So this is 18 divided by square root of 249. I get 1.75. So 9 divided by 1.75 gives me a z-score of 5.14. Do I want a shade norm? No. Why? The z-score is really big, and we actually stop at 5. How much area is there from 5.14 to infinity? 0. It's so small our calculator won't even give us a number. Okay? So in this case, the p-value was 0. What does that mean? We reject the null and we say there is a highly significant difference between a score of 68 and 59. Okay? All right, number 4. Suppose the study in example 4 is repeated on 2,000 subjects with 1,000 assigned to vitamin C and 1,000 to control. Now, what happens when we talk to a lot more people? We get a more exact value because our standard errors get smaller. The more people you talk to, the smaller your standard error, and the more, basically, the more exact you can become. All right. So we have 2 studies where D is 1,000 in both of them. And the average colds for the vitamin C group is equal to 2.4 with an SD of 2.9. And the average for the control group is 25, or 2.5, with an SD of 3. Okay, so once again, my null is that the difference is equal to 0, and the alternative is that the difference is greater than 0. So I draw the normal curve. 0 is the expected value, and we ended up with 0.1. 0.1. Is that difference enough to say that vitamin C helped? That's what we're going to figure out. So I need an SD difference, or an SE difference. So I take the square root of 2.9 divided by the square root of 1,000. Not L1, I want the square root of 1,000. And then I'm going to square that, then add that to the square root of 3. Nope, I lied. Add that to 3 divided by the square root of 1,000 squared. Does everybody understand that? Okay. That gives me 0.13. Okay. Now what do I do? I need a z-score. So my difference is 0.1. Divide that by my SE difference, and I get 0.75. Now, we already know we're going to accept the null because we're smaller than 1.68, but we need to figure out the p-value anyway. Clear the draws, do a shade norm, and I'm going to go from 0.75 to 5. And that gives me a right-tailed area of 22.6%. Is it likely to land at that mark, 22.6%, when we're doing a sample? Yeah, that happens all the time. So is the difference explainable by chance? Yes. 0.1 is close enough to 0 that we say we accept the null, and we say there is no difference between, there's no significant difference between the vitamin C and the control. So did vitamin C help? No, we don't think so. So, and this is, they don't do this in this class, but when you do a study, you determine your p-value beforehand, and it makes more sense to talk about it in certainty. So when you do the study, we're going to say, okay, we want to know, does vitamin C help? we are going to use 90% as our test level. So if I say I'm going to choose 90% as my divide line, which would give a 10% on the right side, then you do your study and you compare your p-value to 10%. You could choose 8% or 6% or 1%, whatever you want to choose. Most people choose 5%. If it was something medical, you would probably say 1%. And you state that at the beginning. Now, let's say that you choose 5% and you do the study, and it ends up that you get 4% as your p-value. And you really, really, really want to accept the null. You can't go back and change your p-value to 1%. That's considered, what's that? That's what you have to do, is redo the study. Now, if I publish a study, how are you going to know that I actually chose the p-value ahead of time? You're not. There's no way to know unless you were involved. So, and the very last chapter in this book talks about hanging data up and beating it with a stick until you get what you want. And you can pretty much, if you look hard enough, you can find what you want in any set of data if you look hard enough. But it's considered bad form to look that hard. And we'll talk more about that in the very last chapter. So the whole 5% window is the standard, but you really can choose whatever number you want. So for instance, I could say I'm choosing 70%, which would put a 30 here. Well, 22.6 landed outside of 30. So I'm 70% certain that the vitamin C test proved that vitamin C helps, right? But if you jump to 80%, now I accept the null and I'm not sure. So it's kind of weird like that. You choose how, you decide how wrong are you willing to be. And it's just a give and take. The more certain you are, then the more realistic the answer is, but the harder and harder it is to prove it wrong. The less certain you are, right, the less sense it makes, but the easier it is to reject the null. Was there another part to this? Why would the averages change from one study to the next? It would just be chance error. That just is the luck of the draw. That's what happens.